In section 5, we're going to go ahead and wrap up topic 6 by not only talking about resonance structures formally, since we've mentioned it already a little bit, but we're also going to take all the concepts we've been learning in topic 6 and we're going to pull it all together in one final way. So recall that a resonance structure occurs when bonding cannot be shown with only one Lewis dot structure. In other words, there are multiple ways to draw a structure. So for example, if I were to ask you to draw nitrate, which is NO3 negative, you would most likely come up with a Lewis dot that looks something like this. But notice the double bond could have been here, here, or here. There's multiple ways. So rather than just drawing nitrate in that one way, we actually need to draw all 3 ways that it can be drawn. Nitrate would have 3 resonance structures. Notice that you have the double-headed arrow that separates every single resonance structure. Remember, you need to draw all resonance structures when a molecule or ion can be drawn in multiple ways. Now, not all resonance structures are created equal. Sometimes they are and sometimes they're not. When the Lewis dot structure has resonance that are equally stable, you need to draw all 3 structures. So how do you know if they're equally stable? Well, let's take a look at the nitrate example that we saw in the previous slide, which is also redrawn here. What helps us figure out stability is the formal charges that we just learned. And let me actually go back because it'll probably be easier to show it here. All these singly bonded oxygens are -1. But do you see how every single ion resonance has -1? There's no other way around it. The oxygen that's doubly bonded is going to be 0, and then the nitrogen is +1, right? So there's nothing different about the first structure, the second structure, or the third structure with regards to formal charges, right? They all 3 have the 2 -1s, and they all 3 have the 1 +1. And they're all on the same atom, oxygen or nitrogen respectively. So if you think about it like that, they're all 3 equally stable. And so when that happens, in this course, you need to make sure you draw all 3 structures. When the Lewis dot structure has resonance structures, but they're unequally stable, I am personally only requiring, in this course, I am only requiring you to draw 1 structure. And if on the exam you draw the most stable structure, you have the opportunity to potentially earn extra credit. So what do I mean by that? If you recall from a previous video when we were drawing the Lewis dot structure for carbon dioxide, remember carbon dioxide could have been drawn with 2 double bonds or with a single triple bond. Both of them are valid Lewis dot structures, but the first Lewis structure has all formal charges of 0. The second one has formal charges of -1 and +1. Out of those 2, which one's the most stable? It's the one on the left. And so if you draw that one, understanding that that one is the best or most stable structure, you have the potential to earn some extra credit. So we're going to wrap up this whole topic with example number 5. And that is, we are going to consider the polyatomic ion phosphate and figure out what would be the best or most stable Lewis dot structure. So starting with what we know, let's go ahead and get the Lewis dot going. So we have phosphorus with 4 oxygens surrounding it. So phosphorus has 5 valence electrons. Oxygen has 6, but there are 4 of them. And then we have a -3 charge, which means I have 3 extra electrons in there. So that's 32 valence electrons. If I do single bonds to every single oxygen, that's 8 valence electrons. So that brings me down to 24. Using those 24, let's take care of the oxygens first. 10, 12, 14, 16, 18, 20, 22, and 24. So I just used up all 24. There's 0 left over. And if I take a look, my oxygens are all happy. And my phosphorus is happy. 8 valence electrons. The only thing left to do is, since it's an ion, I just need to put bracket and then put the charge on the outside. Have I drawn a valid Lewis dot structure? Absolutely I have. I have drawn a structure that has the 24 electrons and all the octet rules are satisfied. But did I draw the best structure? Maybe, maybe not. You may be thinking, well, what else is there to do since all the octets are satisfied? Well, remember, what helps us figure out the best or most stable Lewis dot? It's formal charges, right? So let's go ahead and assign some formal charges. Notice all my terminal atoms are oxygen, and notice they're all singly bonded. Do you remember what the formal charge is for oxygen when it's singly bonded in the outside position? -1. All of them will have a -1 formal charge. And then what about phosphorus in the middle? Phosphorus has 5 valence electrons minus 4 things touching it. So phosphorus has a +1 formal charge. Alright, so let's think about this. Well, my formal charges aren't bad. It's all positive ones and negative ones. But man, every single atom has a formal charge. That's kind of a lot, right? Once again, you might be thinking, what is there that I can do? I don't understand. Well, here's a hint. Is phosphorus eligible for an expanded octet? Can phosphorus have more than 8 valence electrons? Well, let's check. Take a look at where phosphorus is. It is in row 3. So if it's in row 3, phosphorus can have an expanded octet. So, dream with me here a little bit. If I took, and I'm going to arbitrarily choose the oxygen on the left. If I were to take 2 of its electrons and put them into a double bond right here, what would that do to the formal charges? Well, to this oxygen, it would get rid of that negative formal charge because now it's oxygen doubly bonded. And how would it change the phosphorus formal charge? Well, now phosphorus is 5 valence electrons minus how many things are touching the phosphorus? 5 things. I now, by drawing that double bond, was able to get this oxygen as well as this phosphorus down to 0 formal charge, which is a lot better than the -1 and the +1. And I still have my -3 formal charge, or -3 overall charge in the entire ion. Now, that felt pretty good, right? You may be thinking, could we do that again? Well, let's see what happens. Let's say I took these 2 electrons arbitrarily, I'm just choosing this bottom oxygen as an example, and I put it in the middle. What would that do? Well, that would get rid of this negative formal charge, which that would be nice. But now the phosphorus would have 6 things touching it. Now phosphorus has a formal charge again. And phosphorus is less electronegative than oxygens. So should phosphorus, which is least electronegative, should phosphorus have a negative while a more electronegative oxygen be 0? No, that doesn't make it stable. And so we've actually gone a little too far. So I'm going to back it up and bring us back to where we were originally. So once I got the formal charge for the central atom down to 0, I should have stopped right there. This is actually the best structure, the best, most stable Lewis dot for phosphate. But as you can guess, who's to say I had to put the double bond here? I could have done it here, here, or here. So as you can see, there's resonance. And so we need to draw the other 3 possibilities. Now luckily, it doesn't take a lot of work because I know how it should be bonded. I'm just going to change the order of where the double bond is. Make sure that you have the right number of lone pairs of electrons on each drawing that you have. I'm going to go back and fill in formal charges in just a moment. But as I draw each resonance, I just change the position of the double bond. I could probably go faster if I had this on pen and paper. The electronic part kind of takes a little longer. And then I'm running out of space, so I'll put it down here. Although there's not much space down here either. When you do the double bond at the bottom. So there are 4 resonance structures. Actually, technically there's 5, because you can't forget the first one that we had, right? So technically there's 5 resonance structures for phosphate. Alright, so I have my Lewis dots, and then you do need to draw the formal charges on every structure. But I already know every singly bonded oxygen is going to have the -1. So I don't have to redo math, as long as I know that it's the singly bonded oxygens. Alright, so that would be the best Lewis dot structure, the most stable Lewis dot structure for phosphate. Did that take a lot of time? Yeah, a little bit, it did. But that's why you get potential extra credit. So it does come into your favor. And as a reminder, in this course, you get those potential extra credits, but in future chemistry courses, this might be actually just required of you. So it's a good practice to get into right now. That wraps up topic 6. We'll see you in the next topic.